So this was the problem that we had last time. So let me continue with this. We have a round pool, okay, and this is the center. So let me use the same notation here. You are standing at A, you want to go to B, okay. So you are trying to find the right strategy. You first go to, okay, so my notation is that the path is from A to B. You swim here, and then from B to A, okay, say you run, and to C. Okay, so this is pool. Okay, so you swim at A meters per minute. You run B meters per minute. So these are positive numbers. So A, B are positive. Well, they can be 0, then the solution is easy. Okay, so find the path. Find the quickest path, let's say. Okay, so I summarized the whole story in one sentence. So you swim a little bit, and then you run, or vice versa, because you see the problem is symmetric. You can decide to run first. So it's just the symmetric of this. You can run first and then swim. So we are trying to find this point. So apparently that point will depend on this angle. Okay, so let's do it this way. So this is the angle theta. If this is the angle theta, then let us notice that this angle is going to be 2 theta. So, okay, so that helps in finding arc length. Okay, so we calculate the distance AB, multiply it with A, or divide it by A. If one doesn't work, you do the other. Okay, and then you do the same thing with the arc BC. You cover the arc BC with the B minute per second speed. Okay, so you add these 2 times, you get a function that represents your time. Since we'll write everything in terms of theta, as suggested, it will be a function of theta. The limits of theta, you see, theta can be 0, which means that B is equal to C. So you swim all the way. Or the largest value of theta can be what? What can be the largest meaningful value of theta? Of course, theta can be 2,000, but what does it have to do with our problem? In this problem, you see B can move up and eventually B can meet A. In that case, our problem means you run all the way. You don't swim at all. Okay? So in the limit, when the point B goes and touches A, the angle theta becomes what? Am I the only one awake this morning? 90 degrees. Okay? So theta will be between 0 and pi over 2, because you see this line will be tangent here in the limit when this point comes here. So you see that's the usual way of defining tangents. You take a chord and you send the other point to here, so that defines your tangent. Okay, so now let us start with calculating things. Okay, so recall here that time is distance over speed. Okay, so physicists know this immediately, but mathematicians always have to check this. Distance is meter, speed is meter over minute, so meters cancel, minute comes up, so you get minute. Okay, so that's how you do it in the math department. Okay, so we will write this in terms of this. So time required to swim from A to B is AB divided by A, right? The distance AB divided by A. Time required to run from B to C along the arc is length of this arc, BC, so let me denote it like this, divided by B. Okay, so we have to know AB and BC. Okay, so note that this triangle is 90 degrees. Okay, so from high school. Okay. Triangle ABC is right triangle with B the right angle. Okay, so in it, then, okay, so sine, or rather cosine, okay, so because I know this, the radius, let's put this, the radius is R, okay. So in this triangle, this side over 2R is cosine, okay. Cosine theta is equal to AB over AC. Okay, so this is AB. Okay, now I'm not using absolute value. Let us agree this 2R. Okay, so we know that 2R, AB is 2R cosine theta. Okay, so we'll use this here. Now let us look at this. Length of arc BC is, okay, so this arc sees an angle of 2 theta. Okay, so the angle is 2 theta times r. Angle in radians times radius gives you the arc. Okay, so you check it. If the angle is all of this, so it will be 2 pi, then the length will be 2 pi r. Okay, so this is 2 theta r. Okay, so we have these things. Now we have these things. So we can write the time. Total time, we can write it as f of t, because it depends on theta, f of theta. Okay, so this is equal to AB over A. So let me remind what the formula was. AB over A plus BC over B. We know AB, it is 2R cosine theta over A plus 2 theta R over B. And now we need the observation we had. Theta changes between 0 and 2 pi. Pi over 2. Okay. So this is the function to minimize or maximize. Okay. Now we want to find, to minimize this function. Okay, so we take the derivative. Okay, so note f of theta is equal to, you take 2r out, 2r, and now you have cosine theta over A plus theta over B. Okay, so this is our function. Let me repeat that we are only interested in these values of theta. Okay, we take the derivative. F prime theta is equal to 2r times minus sine theta over A plus 1 over B. We want to set this equal to 0. This holds when sine theta equals A over B. Okay? So there will be a critical point if A over B is less than 1. If A over B is larger than 1, then there is no critical point. Then we have to check the endpoints. But at this point, you don't mind. You just check both endpoints and the critical point. Okay? So f of theta, when sine theta is equal to A over B, here assuming A over B is less than or equal to 1. Okay? Otherwise, there is no sign. This is equal to 2r. Okay, so you write a triangle in which sine theta is A over B, then you solve for cosine theta. So what you will get is B square minus A square. Okay, so this is where you need that B should be larger than A, divided by A, plus 1 over B, arc sine A over B, arc sine theta. Okay, so arc sine theta A over B. Okay, so this is the value of the function at the critical point. Then you calculate the endpoints. The endpoints are easy. F of 0. Okay, so f of 0 is 2r over A. Okay, so cosine theta is 1. This is 0. 2r over A. Then you look at f of pi over 2. So this is critical point. At the critical point. So these ones are at the end point. So pi over 2, now cosine pi over 2 is 0. So you have r over, if you put 2 pi here, 2's will cancel, you'll have r over r pi over b. R pi over b. At the end points. Okay, so you have these numbers, you have solved the problem. Now, given the numbers, if AB and R are given, those are the only parameters here. Okay, so you look at these three numbers. Okay, so this number and the other two numbers. Okay, so you look at these three numbers. Okay, so the conclusion is that minimum of these things, minimum of these numbers is the mean of f, and maximum of these numbers is the max of f. Okay, so practically we solved the problem. Now, given the numbers a, b, and r, you just evaluate these numbers and you make a decision. But then, of course, one is curious, can we say a little bit more about this without putting in numbers? How will the answer change when the numbers change? Okay, so we can do that. In fact, we can try the second derivative. You see the function is easy, so we can check the second derivative. Okay. So to continue with our curiosity, consider the second derivative of this. Okay, so this is the function. This is the second derivative. I take the derivative of sine. I get plus cosine. We're keeping this minus. This is constant, so I have minus 2r cosine theta over 2 over a. Where did I find 2 over a? And note that theta is between 0 and pi over 2. I need this. So in this range, cosine theta is positive. Okay, so at the end it is 0, but it is never negative here. 2r over a is positive, so the second derivative is negative here. Okay, so f prime theta is negative. So it means the graph of the function is concave down. This means graph of y equals f of theta is always concave down. Okay, I put an exclamation mark here. So what does it mean? It means that the critical point is always the maximum. Okay, so if you want to take the longest time to reach from A to B under these restrictions, then you have to swim to B first and then run from B to A. That's the longest time. The shortest time will be at the end points. So either this is small or this is small. Okay, so the graph of this will give you the maximum point at the critical point. So let us decide. Okay, so without putting in numbers, we can still continue. By just looking at A and B, we should be able to tell what the strategy is. At this point, we know that the correct strategy is either you swim all the way or you run all the way. Okay, so there has to be a critical point in between where at one point it shouldn't matter whether you run or swim. You should cover the distance in the same time. So that is when these two numbers are the same. Okay. Otherwise, after that point, you start running. Okay, so let's do that over here. Okay. So here I put numbers. Okay, so we don't need numbers. Okay, so the graph of y equals f of theta is one of the following. Okay, so we are roughly speaking now. So this is theta, this is y, and you see it starts from some point, it goes like this, and it ends here. Okay, so this is pi over 2. The critical point is here, and now the minimum point is at the end point. So this means run all the way. Okay, so this means f of this number is smaller. F of pi over 2 is smaller. So this means run all the way. Or it is like this. This is theta. It starts at some point. It goes up and comes down to the same part. Okay. So this is pi over 2 again. Either run or swim all the way. Okay, so when does this happen? This means that r pi over b is strictly less than 2r over a. So this means that both ends are the same. R pi over b is equal to 2r over a, or theta. So now we want, it starts from this part, and now it goes like this. This is again pi over 2. So this is when r pi over b is r pi over b is the endpoint. So this is larger than 2r over a. Okay, so this means a over b is less than 2 over pi. A over b is 2 over pi. And here a over b is larger than 2 over pi. Okay, so this is the deciding criterion. This criterion. Okay, so we didn't have to put in any numbers. So we just made our life easier. We could have stopped here. You just program these. Numbers are given. You just calculate these things. One of them is smaller, and you tell that that's the answer. But after you do this several times, you realize that either this is going to be smaller or this is going to be smaller. You are calculating this thing in vain. It never comes up as a smaller number. Then you wonder, why is this happening? Or maybe I didn't do enough examples. Okay? Maybe you just tried 100 different sets of numbers and only these two showed up. But if you tried 1,000 more, maybe sometimes you would see this. Okay, so this is now the question that comes to mind. So you check this. You suddenly realize that the reason why this is not showing us up as the minimum is that because at every situation, this is the maximum. Okay. Then you realize that the graph must be like this, and this is the deciding criteria. So you just erase this. You write a new program, just one-line program. Just given the numbers a and b, you just check the ratio, compare it to pi over 2, and you give the answer. Okay, so that's the solution of a min-max problem. Okay, any questions, any comments? What would you do, any part of this better than the others? Okay, so this is how I solve this. Okay, so we used to ask this in the midterms because this is a nice example where you set up the function, take the derivative, equate to 0, evaluate the function at the critical point, and then you claim that this is the minimum or maximum, whatever the question asks. Okay, so we ask the minimum, and you evaluate it here, and you say this is the minimum. That's wrong, so it's an opportunity to teach you that checking the endpoints is important. Okay, so this is an example where all the solutions are at the endpoints, no matter what the parameters are. Okay, so that was one interesting problem for me. Okay, now to make you happy, let me solve a numerical problem. Then we'll do non-numerical problems again. Okay, so let's do this one. So this is, I took this from the book. So this is our second problem. Okay, so in this problem we have a river. For some reason it is 2 kilometers wide. Well, I've seen very wide rivers, but I haven't seen enough rivers. So the river I saw was probably around 1 kilometer wide. So this is 2 kilometers wide. There is a point A here. This is the corresponding point here. And 6 kilometers along the way, we have the point B. Okay, so this part is 6 kilometers. So what we want is, in this problem, we want to set a pipeline from here to B, but the cost to traverse the river is, of course, larger than the cost to lay the pipeline on the ground. Okay. So we have this point C, this is x, this distance is 6 minus x. Okay. So cost of the pipeline along the river, so in this case along AC is, so let me see what the book is saying, 800,000 TL per kilometer. On land, so along on land, so along CB is half of this. Okay. So the problem is find C, find the point C which minimizes the cost. Okay, so in this problem, maximizing the cost is easy. Just choose a point far away from both A and B. You get a very large cost. Okay, so minimum is reasonable here. Okay, so we'll find this distance, multiply it by 8. Okay, so we can say the cost will be expressed in 100,000s. So this distance will be multiplied by 8. Then this distance, 6 minus x, will be multiplied by 4. And the problem will make sense when x is between 0 and 6. Otherwise, it will be redundant. We'll take the derivative. Okay. Equate that to 0. And we'll evaluate the function again at the critical points and at the end points and see which one is smaller. Okay, so that's the strategy, the usual strategy to solve min-max problems. Okay, so we have to find this distance. You see that this side is x, this side is 2. So this side is square root 4 plus x squared. Okay, so cost function. So again, I called it x, is f of x 8 times this distance, 4 plus x squared, plus 4 times 6 minus x. X is between 0 and 6. The cost is in 100,000 liras, lira units. Okay. So we take the derivative. So the derivative is f prime x equals 8 will be there, 8x square root 4 plus x squared minus 4x equal to 0. Okay, so that's the derivative. I equate that to 0. 4. Okay. Now we solve this. Okay, so let me solve this here. It's easy. So we have 8x equals or minus 4 or equals 4 times 4 plus x squared divided by 4x squared. So the denominator does not count, does not contribute to being 0. So cancel these things. You have 2 here. Now take square. You have 4. X squared is equal to 4 plus x squared. So you have take this to the other side. 3x squared is equal to 4. X squared is equal to 4 over 3. So x is equal to, okay, so let's go here. So x is equal to square root square root is in the denominator, 2 over square root 3 in the range, in 0, 6. Okay, so here. The other square root is negative, but it's outside. Okay, so that's the other solution will tell me to go from A to this and then go here. So it's probably an inflection point. If you plot the graph of this, you see this function makes sense for all values of x. Just to understand why you had the other critical point, you can plot this function from minus 10 to plus 10. So probably there you will have an inflection point. I didn't plot it, but generally that's what happens. Okay, so in our range, this is the solution. So this is approximately, just to get an idea, this is approximately 1.15. So 1.15 kilometers to this side. So you try to take only a little part of the river. Okay, so what do we do? Now we calculate. You can again check what is happening if x is, at this point you have several things. The easiest thing is to evaluate the function at the endpoints. The other thing is you go to second derivative and check the sign of this at that point. Okay, so that will give you something. Or you can look at the sign of this. Is f prime negative or positive before this and after this? So that tells us if the function is increasing there and decreasing, so that will give you maximum. Or maybe the function is decreasing then increasing, it will give you minimum. Okay, so whichever is easier at this point, you choose that. So let's see what I did. I just calculated these. F of 0 is 40. Okay. F of 6 at the other end point is square root 40 times 8. Obviously, this is not going to be the minimum. It's approximately 51. And at the critical point, 2 over square root 3, you get 8 times 4 plus 4 over 3. So this is 30. So not only this. Okay, so let me just write the answer. The answer after you simplify this is 24 over 3 plus 24. So this is approximately 38. Okay, so you have these numbers. Now you decide that the critical point gives you the minimum. Okay, so this is the minimum occurs at the critical point. Okay, so this is the solution of the calculus problem. Now the question was find the point C which minimizes the cost. The answer that C should be 1.15 kilometers towards B from the point across A. Okay, describe it in any way you like. Okay. Okay. Any questions? Okay, so I think we can solve one more. Okay, next hour we'll also continue, but I'll solve some more complicated problems. Okay, so this one is about the ice cream industry. You want to construct a conical cone, ice cream cone, drinking cup. Okay, so this was problem 2, right? This is then 3. A cone-shaped drinking cup. Okay, so the problem in the book is not ice cream cup, but drinking cup, which is of this form. Okay, is made out of okay, so you have Okay, so you have a circular disk, you have a disk, you cut out a sector of the disk, then glue these parts. Okay, so glue these parts by gluing these parts. Okay, then you obtain a cup. Okay, so what question can we derive out of this? What is a meaningful question? Well, if you say minimize or maximize the surface area, then it's all there, okay? If you don't do any cup, that minimizes the surface area, okay? Again, if you just take the whole circle and pinch a little bit, an epsilon, okay, so that maximizes the surface area. So surface area is not interesting, and then what remains is the volume, okay? So maximize or minimize the volume. Minimum volume, again, doesn't make sense. Well, it makes sense, but it's not interesting. Don't do anything that minimizes the volume of the cup, okay? Because this whole thing, the whole disk, is theoretically a cup with height 0. It has 0 volume, okay? So that minimizes the calculus problem. So a meaningful question will be, how should I cut this so that when I glue them, I get maximum volume, okay? So let us put an angle theta here. So let's call it, I call it theta. So what should theta be? Theta be so there are two questions here. So let me write both questions. So first thing is, of course, we don't have theta. We just have this problem. The first question is, what is the maximum volume? What is the maximum possible volume for such a cup? So this is the first problem. So of course it should depend on R, right? And to get this, or rather, let's say to achieve, to show that we have some vocabulary, and to achieve this maximum, how should we cut the disk? That is, what is theta? What theta will give max volume for the cup? Okay. Okay, so we write the volume of the cone. There are two parameters there. At first, we are discouraged because if you have two parameters, we don't know how to find the maximum minimum. But those two parameters are dependent on each other because you see this side, the radius here, okay? So this side is the same as this side, right? So this side is R, this is R, this is again R. So that's our observation. The volume of the cone depends on its height and its radius. So its radius and its height are the legs of a triangle, right triangle, whose hypotenuse is big R. Okay, so they are related. Okay, now I can write the volume of the cone, which is in terms of small r and h. They are related by the triangle equation. So I have a function of a single variable. Okay, now I am in calculus first semester. Okay, so I take the derivative. I decide what the range of my parameters are, because most possibly I'll end up with a polynomial which has meaning for all values of the parameter, but the values of the polynomial doesn't make sense for me if I let the parameters loose. So for certain values of the parameter, the polynomial I'll have will give me the volume. So I'll decide on that, take the derivative, equate that to 0, find the roots, evaluate the function at the critical points and the endpoints, decide which one is maximum. Okay? So that will answer the first part. Okay, so you see the first part has no theta in it because the height and radius of this is related to r, so everything will be solved in terms of this r. Okay, so once we have this, how shall we obtain theta? Okay, when we solve the maximum volume, so it will be the parameter. The parameter will be either height or radius. So we totally know the shape of the cone. Okay, when you know the shape of the cone, you know this perimeter here. Okay, so this perimeter here corresponds to this perimeter here. Okay, so from that equation, you solve for 2 pi minus theta. So that gives you theta. Okay, so that's the strategy. So this is what you should do before you solve a problem. First, you solve it in your mind, modulo the calculations. Okay, so all that remains is the calculation. In simple problems, it always works. Later on, when you do research or do big projects, so you solve the problem in your head, you start writing it, and lots of problems come up which you didn't think of. So you learn from them. You do this process over and over again. But the most interesting thing is most of the time what you have in mind doesn't work out on paper. But with a cooked up calculus problem, it always works. Okay. So we solved the problem in our minds. So let us continue. So we take this cup. We write it like this. Okay, so this side is r, this is small r, and this is h. This angle we notice is right. So r square plus h square is equal to r square. Okay, and volume of this cone, of this cup, is base 1/3 times base area times height. Okay, so that is traditionally the volume since the ancient times, whatever your shape is most of the time. Okay, so this is 1/3. Base area is pi r square times height. Okay, so you see that I need r square. So if I choose to express r squares in terms of h, that's easier. Okay, you can do it the other way, but then you will have to take derivatives of square roots. Nobody wants it. Okay, so here I have r square is equal to r square minus h square. So volume depending on h is 1/3 pi r square is r square minus h square times h. Okay, so what is the domain for h? Obviously, I want positive h because this is going to be height. Okay, I don't want negative thing. So these things are related here. Here h cannot be much larger than this r, okay, because I'll take the square of this, add something. Okay, I can add 0 here, but h can be r at maximum. So this goes up to r. I know immediately that the endpoints will give me 0 volume, so the endpoints will not give me minimum. If I find critical points, the minimum will be one of them. Okay, so note immediately that from this V0, because of this is 0, and VR, because of this part, is 0. Okay, so endpoints will not give the maximum, the max volume. Okay, now what remains is to take the derivative of this. Okay, so let me erase this. We'll take the derivative, equate that to 0. Now we are confident that if we get only one critical point, that's going to be the maximum. If we get two critical points, then either both of, one of them has to be an inflection point, okay? It can't be, if it goes up, goes down, if this is going, if this is going to be local maximum, then it has to go up, but then eventually it has to go to 0. That will contribute another critical point. So we know that, okay, let's check how many critical points we have. Okay, so let us write VH. So VH is equal to pi over 3, this is constant, and I have r square h minus h cube. Okay, so I have V prime h equals pi over 3 2rh minus 3h square. I want this to be equal to 0. Okay, so this part is 0. I can take h out. 2r minus 3h equals 0. Okay, so we have only one critical point inside the interval. The other critical point is at the end point, as far as we are concerned. Okay, so h equals 0 is an end point, so we ignore it. So we ignore it in this problem. Okay, so the reason was V0 is 0, not maximum. Okay, so the other critical point is h equals 2 over 3r. Okay, so that is well inside the So why is my derivative here different than the derivative I took at home? Yes. Okay, so let's continue from here. Okay, so this is r square minus 3h square. So this is now easier, equal to 0. So h square is equal to r square over 3. I'll take the square root in this interval, so I need positive square root. Okay, so h is equal to r over square root 3 in our interval. Okay, so as we mentioned, we have now only one critical point, so it must be maximum, because at the end points we get 0. So we check to double check. So this must give the maximum point, since VH is always positive and equals 0 at the end points. Okay. To double check, you look at the second derivative of this. So this is minus pi over 3 6h. Okay, so this is what? Minus 2 pi h. This is negative. The graph is concave down. So the critical point gives you maximum. Okay, but this was to double check, just to check. derivative correctly. Since I made one mistake, now I need to check this. So, okay, so maximum volume is V R over square root 3. So you calculate that. So let me write 2 pi over 9 square root 3 times R cubed. Okay. Okay, so this is in R region because I'm dividing R by a number larger than 1. So H is less than R. It is positive. Okay, so let's find theta after the break.